Good morning. Welcome to course Radiation Oncology Physics, and now we are running in the fifth week of our course, and today the lecture is 22, and in this fifth week we are discussing the brachytherapy, various physics technology behind the brachytherapy application in radiation oncology. And learning objective of our today's class is definition, the dosimetry systems under which we will discuss the Quimby system, memorial system, the Patterson-Parker system, the Paris system. We will also discuss surface mold type of brachytherapy with this class, and we will discuss the methods of source localization. Now, as I have mentioned in the previous class where we have discussed the principle of brachytherapy, we have discussed the definition of interstitial brachytherapy. Interstitial brachytherapy, where we apply the radioactive isotopes directly within the tumor volume. So, radioactive isotopes are directly implanted within the tumor volume. You can see from this figure that in the hair, one carcinoma breast patient, where we apply, these are the applicators, and these are the tubes we have applied within the target volume, and this is the placement, and we have open this one and remove the tumor, and we place the radioactive isotopes, and these are closed, and we get this type of applications, and we can give the radiation by these tubes, and radioactive isotopes is connected. These tubes are connected with our brachytherapy machines, and we treat according to our treatment plan. So, this is the interstitial brachytherapy, where radioactive isotopes are directly implanted within the tumor volume. So, you can see that this is a very skillful procedure, where and very much we need to be very much accurate to apply all these applicators, and as we are treating human being, so for their betterment, so we need to very much accurate, and we need to very much cautious, so that there should not be any hazards or complications for the patients. And you can see this is the final results of the treatment of our brachytherapy. Now, interstitial brachytherapy, we need to have a very objective or very specific type of treatment planning. We have discussed the type of treatment planning in our external beam radiation therapy, where we have discussed various technological, physical aspects of treatment planning of external beam radiotherapy. Now, we are going to discuss the dosimetry systems or dosimetry system, that is treatment planning of interstitial brachytherapy. So, objective of the treatment planning of interstitial brachytherapy, we need to determine the distribution type of source, distribution and type of source, means how we will place our radioactive isotopes, and what type of radioactive isotopes needed for this particular type of disease or for the particular type of lesions. So that we will get a optimum dose distribution. So, this is here we have judiciously used this optimum term, because there are some benefits and there are some complication of radiation applications. So, we need to justify our dose distribution. The dose distribution should be in direction towards the cure of the cancer patients. So, first objective is to determine the distribution and type of source to provide a optimum dose distributions, and second, our treatment planning objective is to provide a complete dose distribution in the irradiated volume, means our target volume, we need a complete target volume, and the volume which is radiation, which received the significant amount of radiations, that is irradiated volume. So, we need a complete dose distribution in the irradiated volume. Now, we have various type of dosimetry systems which are applicable for interstitial treatment planning. They are Quimby system, the Memorial system, the Patterson-Parker system and the Paris systems. So, these are 4 type of dosimetry systems are applicable for interstitial brachytherapy application. Now, discussing the Quimby system. This Quimby system is developed by Edith Quimby et al. And this is the I think this is oldest one. So, their Quimby system describe the dose distribution, source distribution, that they described, they recommend that source should be distributed equally spaced. They should be equally spaced. Here you can see a distributions. They are actually where of which are applied in the patient, and this uniform distribution of linear sources. So, we distribute the radioactive isotope uniformly throughout the target volume, and because of uniform source distribution, we will land up with a non-uniform dose distributions. Now, we will get a higher dose in the central region and a lower dose in the peripheral region. And Quimby system, they propose that they propose the dose prescription approximately 5000 R to 6000 R in 3 to 4 days. Now, how this amount of dose is delivered and how this what is the time of implant, what is the time treatment durations of the implant. So, we need to they have given a Quimby tables. These tables gives us the amount of milligram hour required for delivering of 1000 Ranjan in the center of the treatment plane, and this type of table gives us the dose of up to the 3 centimeter from the center of the treatment plane. So, the main point of Quimby system, they are equally spaced and the sources are uniformly distributed throughout the target volume, and because of this uniform source distribution, we will get a non-uniform dose distribution, and where higher dose is central region and lower dose in the peripheral region. Now, coming to the Memorial system, this is the extension of Quimby systems, and this is proposed by Lagulin et al. And they recommend that the source distribution is equally spaced and approximately 1 centimeter apart, and they have also recommended to uniformly distribute the linear sources, but they generate the dose distribution by the help of computer. And as we distribute the linear sources uniformly throughout the target volume, so we will get a non-uniform dose distribution, and where higher dose in the central region and lower dose in the peripheral regions. And they also modified the Quimby tables, and these tables, updated Quimby tables, gives the amount of milligram hour of radium. This is the time where we use the radium for brachytherapy applications. So, every tables were given in terms of radium for the radium isotopes, radioisotopes, and this milligram hour, amount of milligram hour radium is required for the delivering of 1000 rads in designated points. These are the two things where in previously Quimby he recommend that 1000 R. Now, here the Memorial system, it is the extension form of Quimby system, 1000 rad in some designated point, and in previously we define the dose at central plane, and there are some terminology, minimum peripheral and reference maximum dose. These are the terminology where the dose is excessively dose to the central region can be limited. Now, coming to the dosimetry system, this is the Patterson-Parker system or Manchester system, and this is a very important dosimetry systems which is used many years after these Quimby system and memorial systems, and this Patterson-Parker system is developed by Ralston Parker. He is a radiation oncologist, and Herbert Parker, and he is a radiological physicist. So they developed the Patterson-Parker system, and this is also known as the Manchester system. This is also known as Manchester system. They recommend the dose distribution equal spaced. They also recommend 1 centimeter apart, and maximum in 1 centimeter apart, and non-uniform distribution of linear sources. In earlier, we uniformly distribute the radioactive isotopes. Now, this Patterson-Parker system, they recommend the non-uniform distribution of linear source. Now, because of this non-uniform source distributions, there is some rule which I will discuss in later slide, and non-uniform distribution of source will get a uniform dose distribution throughout the target volume, and even we achieve the uniformity from plus 10% plus minus 10%. So, this is a very good uniformity in terms of brachytherapy applications. So, they also given some tables, they are known as Patterson-Parker tables, which gives us the amount of radium. Again, it is the era of radium applications, and where the amount of milligram hour of radium required for 1000 rad in prescription point. So, this is the dosimetry system they define as a Manchester system, and this dosimetry system is developed by Ralston Patterson and Herbert Parker. So, difference is non-uniform distribution of radioactive isotopes, and because of this non-uniform radioactive source distribution, we will get a uniform dose distributions, and uniformity we achieve plus minus 10%, and they have also given the tables where we can determine the amount of milligram hour of radium required for 1000 rads in prescription point. Now, the Patterson-Parker's rules, we are discussing the planar implant. So, planar implant where we uniformity achieved in parallel planes at 5 centimeter from the implanted plane. If this is the implanted plane, we can achieve the uniformity 5 centimeter above and 5 centimeter below, means we can effectively uniformly treat of 1 centimeter of tissues by this Patterson-Parker system, where we achieve a plus minus 10% of uniform dose uniformity. Now, the distribution rules are they mentioned that the ratio of amount of radium of periphery and central area, it's dependent on the size of the implant. They define this is the size of the implant, how much amount of activity we want to we have to apply in periphery and center, so that the whole implant area will give a uniform dose distribution of plus minus 10%. And they given the table that if the area is less than 25 square centimeter, if our target area is less than 25 square centimeter, we need to apply the 2/3 of the radioactivity in the periphery. We need to use 2/3 of the activity in the periphery and 1/3 in the core or central regions. Now, if our if our target lesion is 25 to 100 square centimeter, then we have to apply the half of the radioactive isotopes in the periphery and half in the center. Again, if the radioactive target lesion is more than 100 square centimeter, then we need to apply 1/3 of the radioactive isotope in the periphery and 2/3 within the center. And by this distribution rule, we can achieve the uniform dose distribution within the implanted volume. And spacing of the needle is equal and not more than 1 centimeter. They have defined that this should not be more than 1 centimeter. Now, if one end is uncrossed, here you can see we have two type of implant. This is first type where both ends are crossed by needles. But in this type of implant, this end, the upper end and the lower end are uncrossed. Now, if we have a uncrossed end, then the effective area will reduced by 10% for each uncrossed end. Now, here we have two uncrossed end, so effective area will be reduced by 20%, 10% for each. Now, the dose distribution will be like this. They will be dip here because of uncrossed end, they will be dip here, and they will, this is the distribution we will get from this type of radiation implant. Now, this from this implant we can see, we can have a this much area we can effectively irradiate. Now, if we apply multiple plane of radium, the radium should be arranged from rule 1, 2 and 3. We can apply multiple plane to treat the tissue volume more than 1 centimeter. Then we need to apply multiple plane. Now, considering the volume implant, because sometimes we need to have 3D volume, and these volumes are regular volume they considered, and they are cylinder. They may be the volume may be sphere or may be cuboid in shape. Now, they define the distribution rule for volume implant. First, you need to divide your radioactive isotopes in 8 parts. You need to divide in 8 parts. The amount you have, you need to divide 8 parts. Now, if it is cylinder have 3 type of part. One is belt, another is core, and we have 2 end. So, in cylinder we need to put 4 parts out of 8, and core we need to keep the 2 parts out of 8 and 1 part for each end. Now, if the volume implant is sphere, then there is in volume we have a cell and we have a core. The cell will get 6 parts and core will get 2 parts. And if the 3D volume is cuboid, then each side will get 1 part. So, we have in cuboid we have 6 side. So, 6 part we utilize for side and we apply 2 parts in the core. So, this is the application distribution rule for the regular type of volume implant. Regular type means cylinder, sphere or cuboid. And again the needle spacing should not be more than 1 centimeter. And in the uncrossed end, the volume will be, effective volume will be reduced by 75% for each uncrossed end. Here you can see this end is crossed and this end is uncrossed. So, we need to reduce the effective volume, irradiated volume by 7.5% for each end. Now, we will discuss the Paris system dosimetry system for the interstitial brachytherapy. And this Paris system is most of the time is currently very popular form of dosimetry systems, which is applied in various kind for interstitial brachytherapy. And this Paris system is developed to intend for long source, because after time the brachytherapy applications, peoples are using brachytherapy for larger volume, and we will get there are very much development in source construction. So, iridium 192 wires are available for brachytherapy applications, and iridium 192 is the radioactive isotopes which very much fit in the gamma energy of 0.38 MeV, which is within the range 0.2 to 0.4 MeV of ideal brachytherapy sources, and it has a half life of 74.8 days. So, iridium 190 wires are used for temporary applications, interstitial applications. And here we have a relaxation of source spacing more than 1.5 centimeter, and this is defined, this Paris system is defined for large treatment volume irradiation and sources having uniform linear activity. We need to apply the uniform linear activity, and for each applications, if we use the source spacing of 1, we need to keep this one source spacing for whole the application. We can use 1.5 for different patient, and these linear sources implanted in parallel lines. And dose specification, this is the first system where dose is specified based on isodose surface. They are based on isodose surface, and this is which isodose surface? This dose is specified on isodose surface of reference dose. Now, reference dose is defined as the 85% of basal dose. Now, here in diagram we will describe how we define the basal dose. In single plane, if these are the radioactive wires are placed, and these red points are the basal points, these are between the midway of each of the pair of the wires. These are the basal points. So, these red one are basal points, and we need to average out this basal dose, and out 85% of this dose we consider as a reference dose for this implant. Now, if we apply two plane and we have a triangular geometry, then center of gravity of each triangle is considered as this. These are the basal points, and the dose of all these is sum and average out, and this basal dose is considered is 85% of this basal dose. Average basal dose is considered as reference dose, and the isodose surface of reference dose will consider for this type of applications. Now, if we apply two plane and square geometry, the center of each square is considered the basal points. These are the basal points. These are the basal points. Now, surface mold, this is a different kind of brachytherapy applications. These are surface molds are applied for treatment of superficial targets, and we create or we prepare the plastic mold to conform the patient contour, and sources are secured outer side of this mold, and source to skins, we have a source to skin surface distance is normally 0.5 to 1 centimeter. So, because of this distance, we will get a good dose distribution of superficial lesions. Dosimetry rules are almost similar for similar as per interstitial brachytherapy we have applied. That means we can apply the Quimby system, the Memorial system, the Patterson-Parker systems, or we can apply the Paris system for these surface mold type of dosimetry. Now, you can see these are surface mold. They are prepared by dental material, and the applicators are applied outer side of this mold, and this mold is just conform the contour of this patient surface, and we can treat as per our requirement. You can see from this figure, this is the lesions we want to, superficial lesions, this is nose region we want to treat, and these are the tubes applicators which are applied outside this mold, and this mold is conform this contour of this nose, and we can apply like this, and these tubes are connected to our brachytherapy units, and this is all about surface mold. Now, we have applied the radioactive isotopes, and we need to localize the isotopes for our dose calculations, and so we need to localize this implant, we need to have the x, y and z coordinates of radioactive isotopes in patient body, and these x, y, z coordinates is calculated from various methods. We will discuss on most popular methods. First one is conventional methods, that is conventional that is orthogonal X-ray imaging, by which we need to take the X-ray images from anterior posterior sides and AP directions, and we need to take a X-ray images of lateral, means 0 degree and 90 degree angle. So we will get in this AP film, we will get the X and Y directions, and in the 90 degree lateral image we will get, this is the AP, we will get the X and Y coordinate, this is the AP film, and from this lateral film we will get the Y, sorry, this is X and this is Y. So in this film we will get the Y and Z coordinates. So we will get X, Y and Z coordinates by combining these two radiograph, and this we can done, we can calculate by manually, or we can perform the dosimetry or applications treatment planning by using the computerized system. But nowadays we are using almost up to 30 radioactive isotopes applicators. So this is very complicated to retrieve all these points, all these reconstruction is very complicated. So nowadays we are using the volumetric imaging like CT or MRI. So from this we can retrieve the volumetric data and we create our treatment plan according to our requirement, and we can position the radioactive isotopes as per our requirement, and this is purely computerized system, and we are using a very sophisticated and very accurate treatment planning systems for brachytherapy applications. You can see these are the positions, the black points, these are the source locations, and these green and red lines, they are isodose lines which are generated by the computer calculations. So we can very effectively irradiate and we can localize the high dose radiation to the target volume, and we can treat the patient towards their directions of cure. And this is all from today's class, interstitial brachytherapy, and thank you all once again.